Welcome back everyone. So, we discussed diagonalization in the last class. So, let me continue that. So, as I told you before, so there is a hope for looking for simpler form of a given matrix with respect to some coordinate system. So, let me recall the proportion that I stated last time. So, let us take T be a linear operator on V and assume that the dimension of the vector space is finite dimensional. So, now we are actually able to write V as direct sum of indecomposable T invariant subspaces. So, there exist V I, each one is indecomposable and T invariant subspace such that we can write V as direct sum of this. So, recall that V I is said to be indecomposable T invariant subspace if it cannot be written as direct sum of two proper non-trivial subspaces. Suppose you write V I equal to some W 1 direct sum W 2, then that should imply that W 1 is 0 or W 2 is 0, where both W i's are T invariant subspaces. Okay, so why such decomposition exists? So, this is as simple as writing a number as product of prime numbers. So, we can actually induct on the dimension and prove this. So, if the dimension of the vector space that we started with is 1, then there is nothing to prove because the space itself is indecomposable space. So, let us assume that the dimension is more than 1. So, in that case, if V itself is indecomposable, then again there is nothing to prove. So, otherwise what happens? Otherwise there is only one option. So, it should be decomposable. So, then we can write V as some direct sum of T invariant subspaces W 1 and W 2. So, both W i's are T invariant subspaces. So, now since both W 1 and W 2 are non-zero and both W 1 and W 2 must be proper inside V. So, that would imply that the dimension of W I is greater than or equal to 1 and less than dimension of V. So, now what we can do? We can actually just restrict our operator to W I, because this is indeed T invariant subspace. So, we have an operator acting on W I, and now note that dimension of W I is strictly less than dimension of V. Now, by induction we see that W i's can be written as direct sum of indecomposable T invariant subspaces. So, W I can be written as direct sum of T invariant subspaces of W I, and it is easy to prove that any T invariant subspace of W I will be T invariant subspace of V. So, you can just put them together and then get V as direct sum of T invariant subspaces. So, you can write this as direct sum of T invariant subspaces, this as direct sum of T invariant subspaces. So, putting them together you can write V as direct sum of indecomposable T invariant subspaces. Okay. So, this is indeed, even though looks somewhat very simple result to prove. So, this is actually backbone of looking for all possible canonical forms. So, this in a way guarantees that we can look for something simpler. Okay. So, we can look for a basis, with respect to that basis the matrix of the linear transformation looks somewhat simpler. Okay. So, with this with this we can actually hope for something better. But here, so we wanted to write given vector space as T invariant subspaces. Okay. So, this result indeed guarantees theoretically that it can be achieved, but computationally we need to look for some algorithm so that we will be able to actually achieve this. Okay. Otherwise, there is no use of this. So, that is what we want to do now. So, our task is to actually achieve this decomposition. In order to achieve this decomposition, our first task should be looking for T invariant subspaces. So, let us look for first T invariant subspaces. So, because if we do not have enough T invariant subspaces, then there is no point. So, how do we get T invariant subspaces? So, for that we have this very simple strategy. So, we can take another operator, call it capital S, such that this operator actually commute with the original operator. So, T is fixed, so T is coming from this endomorphism of V, where the dimension of V is finite. So, you take another operator which actually commutes with T. So, then it is easy to prove that the kernel of S is indeed T invariant. And this is very simple checking. For example, if you start with a vector in kernel S, then that simply says that SV is 0. Now, you apply T. So, then TSV will be 0, but TS is same as ST. So, that implies that STV is 0. So, you just switch S and T. So, then you get STV 0. That means S of TV is 0. So, that means simply TV is in the kernel S. So, that means kernel S is T invariant. So, this is one way of actually getting T invariant subspaces. So, this is the motivation in defining eigenspaces, generalized eigenspaces and so on. Now, how do you find an operator that actually commutes with the given operator T? So, we can simply take T, T square and so on. So, basically the algebra generated by T inside endomorphism of V. So, which is nothing but the polynomials in T. So, this is the set of all polynomials in T, and this is indeed a subalgebra of this endomorphism of V. So, then this is going to actually commute with T for sure. Okay. There could be more elements, but at least for sure we can know that these operators which are polynomial in T will definitely commute with T. So, we can actually slightly generalize this. Instead of taking kernel S, what one can do, one can actually take the following generalized version of this construction. So, which is maybe let us call it Vs. So, you can actually take all possible vectors such that those vectors which are killed by some power of S. So, S power Rv is 0 for some R in Z plus. So, for me Z plus the set of all non-negative integers. Okay, and it is easy to prove that Vs is indeed T invariant. So, basically these two exercises, they are the motivation to define the eigen values and eigenvectors. So, if you are looking for something very simple that commutes with t, I already told we can take polynomials in t, but among the polynomials the most simplest polynomials are the linear polynomials. So, we can simply take S to be some t minus lambda I, and then definitely the kernel of S is going to be t invariant. But we are not interested in some general t invariant space, sorry, we are not interested in 0 t invariant space. So, we expect this kernel of S to be non-zero. So, this actually motivates us to look for lambda in C such that the kernel of t minus lambda I is non-zero. So, this motivates us to look for lambda in C such that the kernel of t minus lambda I is non-zero. And a moment thought will tell you that this is equivalent to saying that this operator t minus lambda I is not 1 to 1, but since it is defined on V, this is same as saying that this is not invertible, and this is same as saying that in terms of the determinant, which can be computed easily, the determinant of t minus lambda I is non-zero. Okay. So, what we can do, like we are looking for some lambda such that this t invariant space is non-zero. So, that amounts to saying that the determinant of t minus lambda I is non-zero. So, this is how we can actually define the characteristic polynomial of t. The characteristic polynomial of t is defined to be the determinant of t minus lambda I. Since this is a polynomial in lambda and has degree n, okay, so we are working over complex numbers using the fundamental theorem of algebra. We know that there are roots for this characteristic polynomial. So, now using those roots we will be able to achieve these non-zero t invariant subspaces. So, these spaces are called eigenspaces and the corresponding lambda will be eigenvalue. Okay, lambda is said to be eigenvalue if the determinant, sorry, so this is supposed to be 0, the determinant should be 0 if the determinant of t minus lambda I should be 0, and you say the corresponding the kernel space, the kernel of t minus lambda I as eigenspace, call this as eigenspace. Okay. So, this is actually called the characteristic polynomial of t. Okay, I am mixing the notation. So, this is should be written as chi t of x or lambda. Okay. So, now as before using this second exercise we also can define something larger than this eigenspace. So, we can define this generalized eigenspace. So, what is it? The generalized eigenspace corresponding to lambda is defined to be as V lambda. So, this is consisting of all vectors in V such that some power of this t minus lambda I kills that vector for some r in G plus. and it is an easy exercise. Maybe I will prove on the way. So, one can prove that the generalized eigenspace is going to be the kernel of t minus lambda I power m lambda, where m lambda is the multiplicity of lambda in the characteristic polynomial chi t of lambda. Okay. So, this is some basic fact from linear algebra. So, let me define what is called the minimal polynomial of t, and that plays very important role in the primary decomposition and so on. So, we have this natural algebra which is generated by t inside the endomorphism of V, and that can be obtained by evaluating this x by t. So, you define this algebra homomorphism C algebra homomorphism from C x to endomorphism of V, that is defined by x goes to t, which is evaluating x at t, and then 1 goes to 1. So, now the image of this C x is nothing but the set of all polynomials in t, and it is not difficult to see the kernel of this map, let us call it pi t. So, this is indeed an ideal inside C x, and this ideal is generated by a unique monic polynomial. So, let us say it is generated by the unique monic polynomial, let us call it m t of x. So, this is called the minimal polynomial of t, this is called the minimal polynomial of t. And the importance of this minimal polynomial, you can characterize the diagnosable operators or the semi-simple operators by having distinct roots for the minimal polynomial. So, here is the big theorem, maybe I will outline the proof of this theorem. So, an operator is diagonizable or semi-simple if and only if the minimal polynomial m t of x has no repeated root. So, it has no repeated roots. So, this can be proved using Jordan-Chevalier decomposition, that can be obtained by primary decomposition theorem. So, let me just quickly state and outline the proof of Jordan-Chevalier decomposition. So, here is the Jordan-Chevalier decomposition. Of t. Again, as before, let us fix this operator t, which is defined on the finite dimensional space. So, we want to decompose this t as sum of two operators which are somewhat simpler than t. Okay. So, let me first recall what is semi-simple. So, you call an operator semi-simple if it is diagonizable. You call some operator nilpotent if there exists some r in n such that t power r is 0. So, these are the definition of semi-simple and nilpotent operators. So, let us say t is given to us. So, then the Jordan-Chevalier decomposition guarantees that there exists unique semi-simple and nilpotent operators, let us call them T s and T n inside endomorphism of V, such that this T can be decomposed as sum of these two operators. So, here T s is semi-simple and Tn is nilpotent. And not only that, both Ts and Tn, they commute with each other, they commute. So, moreover, what we can do, we can actually locate some polynomials Px and Qx without constant terms. So, they live in this xCx such that this Ts can be written as the polynomial in T, P of T, and Tn you can again write it as polynomial in T as Q of T. Now, this immediately implies that both Ts and Tn, they commute with T. So, this immediately implies both Ts and Tn commute with T. So, all these three operators commute with each other, and this decomposition that we have here is called Jordan-Chevalier decomposition. So, this is indeed very important decomposition theoretically, and one can prove this using primary decomposition theorem. So, let me just quickly sketch the proof. Okay. So, one can actually start with the polynomial that is divisible by the minimal polynomial. So, we already know that the minimal polynomial divides the characteristic polynomial, but everything can be proved using primary decomposition theorem. So, let me not assume that result. Maybe I will start with the minimal polynomial of t and then work with that. So, let us take this mt of x. So, this is the minimal polynomial of t. So, now what I want to do, I want to just write this as product of linear factors. So, then I just collect the same roots and then we say that lambda I appears with the multiplicity mi. So, where mi is the multiplicity of lambda I in mtx, and this can be achieved because we are working over complex numbers. So, the only thing that is needed for us is actually the operator t should have all the eigenvalues inside your field. Okay. So, all these arguments will go through. So, that means the characteristic polynomial of the operator should have, or the minimal polynomial should have all the roots in your field, and that is guaranteed because we are working over complex numbers. So, now we have this minimal polynomial decomposed into linear factors. So, using these linear factors, we can actually define these invariant subspaces. They are the generalized eigen spaces, and it is not very difficult to prove that this V indeed direct sum of these generalized eigenspaces. So, this is what called primary decomposition theorem. So, this is what primary decomposition. So, this just uses the fact that lambda is are all distinct. So, in particularly, so we have to consider different polynomials. For example, if we take mtx divided by x minus lambda I power mi and x minus lambda I power mi, they are relatively prime. Okay. So, they are relatively prime, and similarly such arguments, okay, can be used in order to prove this. V can be written as direct sum of V's. So, now what we are going to do, so we want to locate these polynomials p of x and q of x. Okay. So, we will explicitly locate it using Chinese remainder theorem. So, now what you do, use Chinese remainder theorem and locate the polynomial p x in C x such that this P x is congruent to lambda I modulo x minus lambda I power m I, and for each I. Since x minus lambda I power m I, they are all mutually relatively prime for all I equal to 1 to k. So, one can use Chinese remainder theorem to locate this P of x. Since we wanted this P of x to have constant term 0, so we will add one additional relation. So, this P of x congruent to 0 modulo x. Okay. So, let us call this is 1 and then this is 2, and this 2 is actually extra if we have one of the lambda i's are 0. So, if one of the lambda is 0, so then 2 is extra, but that is okay, it does not spoil our motivation. So, since x and x minus lambda I power m I, they are all like mutually relatively prime, we will be able to locate such polynomial. Now, what we do, we just set q of x to be x minus p of x. So, now it is clear that x is nothing but p of x plus q of x, and we define T s to be p of t and then T n to be q of t. So, from this you can easily see that t can be written as T s plus T n, and all this t, T s, T n, they all commute with each other. Okay. So, all these things are now easy to verify, but the only thing that is remaining is to check whether this is diagonalizable or not and whether this is nilpotent or not. Okay. So, if we prove they are diagonalizable and nilpotent respectively, then we are done. So, just look at this equation 1, and then from this you can see that when we take p of x minus lambda I, that is nothing but multiple of x minus lambda I power m I. So, p of x minus lambda I is nothing but some multiple of x minus lambda I power m I, and it means if you evaluate p of t, then minus lambda I. So, this is going to be some g of t times t minus lambda I eigen power m I. So, in particularly if you take this T s restricted to V I, recall V I is nothing but kernel of t minus lambda I power m I. So, in particularly this is going to be equal to lambda I times eigen t, because this part going to go equal to 0 on V I. Okay, that means T I restricted to V I is nothing but scalar matrix lambda I. So, this implies that T s is diagonalizable, as V is nothing but V 1 direction etcetera direction V k. You can put together the basis of V i's and then you can make a basis of V with respect to that basis. The T s is going to look like lambda 1 etcetera lambda 1 and lambda k etcetera lambda k, which is diagonal. Now, let us look for this T n, which is nothing but t minus p of t. So, let us restrict this to V I. So, then this gets restricted to V I, and you can see that t restricted to V I is nothing but p of t restricted to V I. So, this is t restricted to V I minus lambda I eigen t restricted to V I, because p of t is nothing but lambda I on V I. Okay. So, this implies immediately that T n power Mi is 0 on Va. Now again V is direct sum V1 etc. Vk, that would imply immediately that Tn is nilpotent. Okay, this proves actually both Tn and Ts they satisfy the necessary condition that are required, and uniqueness just follows from the properties of Tn and Ts and Tn. Suppose if you write T as S plus n, which is equal to Ts plus Tn, and this is semi simple, let us say, and this is nilpotent, then you can rewrite this equation as follows. From this you can collect the semi simples in one side, Ts minus S, and then nilpotent one side, and note that it is easy to see all these operators that are appearing here, they commute with each other. So, S and N commute with each other. So, this property is very important. So, with respect to the property A, so they are unique. So, basically they commute with each other, that is part of the property of the decomposition Ts and Tn. Okay. So, in particularly S and N commutes, and note that S and N commutes. So, now if you think about it, Ts is polynomial in T and Tn is polynomial in T. So, if Sn commutes, that would imply that St commutes. So, here I am using this commutator notation, the bracket AB means AB minus BA. So, now because of this you can see that Ts and S commute, as Ts is polynomial in T. Similarly, Tn and N commute, and you have semi simple operators, commuting operators, and similarly you have commuting nilpotent operator. So, that implies that the difference between these semi simple operators must be semi simple, and here the difference between nilpotent operator also must be nilpotent. So, you have this side is semi simple and this side is nilpotent, and you have an operator which is both semi simple and nilpotent, that must be 0, there is no other choice. So, this proves the uniqueness of the operator. So, this means we have very nice decomposition of given operator as semi simple operator plus nilpotent operator. So, if you want to achieve, for example, Jordan canonical form, then this actually tells you that you can focus only on the nilpotent operators and then try to prove Jordan decomposition exists for them, Jordan canonical form exists for them. Okay, I will discuss more about Jordan canonical form in the next class. I will stop here for today.